Hello class, this is going to be our flipped classroom on phase change diagrams. Specifically, I'm going to show you a phase change diagram for water, which is also called a heating curve. As always, feel free to pause this video to take notes. So what do we see here when we're looking at a phase change diagram? Well, as you can see by the X and Y axis, I have on the X axis something called heat. And the units I'm using for heat are joules. Now, I don't have to use joules. I could have used calories or some other heat unit. And to be honest, it doesn't even have to be heat. I could have used time. But I prefer to use heat for this example. And the y-axis is temperature, and I'm going to use degrees Celsius as my units for temperature. And I'm starting at a temperature of well below zero, -10 degrees, and I'm going to raise it up to 120 degrees. And we're going to see what happens to water at these temperatures. So first, if we're starting at -10 degrees, well, how would we describe water at that point? Well, clearly it would be a solid block of ice. So let's just write here the word solid. Ice is a solid at that temperature. And it will stay a solid until it reaches 0 degrees. Once it hits 0 degrees, something happens to the ice. At that point, it begins to melt. It doesn't completely melt, it starts to melt. So this part of the diagram is called melting. But there's a fancy word for melting in chemistry. It is called fusion. So going in this direction is melting or fusion, F-U-S-I-O-N. Once we get to this point right here, we are now done with melting. That flat line is done. And we are now in the liquid phase. And as you can see, we're in liquid phase all the way up to 100 degrees. Once we hit 100 degrees, water begins to vaporize. So we call this vaporization. And a fancy word for vaporization is boiling. Actually, boiling is the simpler word. Vaporization is the fancier word. So going this direction would be vaporization or boiling. And then finally, once we get to the end of this point right here, we are now in the gas phase. So there we have the different phases and two phase changes, fusion and vaporization. But what if we went the other direction? What if we started as a gas and went down the staircase? Well, from gas to liquid, we call that condensation. That's going in that direction. And from liquid to solid, we call that, well, there are three different names for that. We could either call that freezing. We could call it solidification, because you're turning it into a solid. Or since most solids form in the form of crystals, we could also call it crystallization. So those are the different terms. So let me show that to you on a different page. Here are the different terms that I just described. We have fusion or melting, which is from solid to liquid, vaporization or boiling, liquid to gas, condensation, gas to liquid, and we have freezing or solidification or crystallization, which is liquid to solid. Now there are two other phase changes that I can mention that cannot easily be described using this picture. What if we started as a solid and jumped all the way to the gas phase without becoming a liquid? Well, that would be called sublimation. Sublimation is the process of going from solid directly to gas. And there are only a handful of substances that can actually do this, that can sublime. The ones that can sublime, hold on, let me sharpen that a little bit, are dry ice, which is also known as carbon dioxide in the solid form, and iodine, which is the formula I2, again, in the solid form. Dry ice and iodine are two substances that can sublime at room temperature. So please make a note of that and memorize those two substances, the two substances that naturally sublime. The opposite of sublimation is deposition. That means going from gas directly to solid. Now, some other terms I want to point out. Exothermic and endothermic. We've learned about those terms before in a previous video. Exothermic means heat released and endothermic means heat absorbed. What phase changes are exothermic and what phase changes are endothermic? Well, the exothermic phase changes are condensation, freezing, and deposition. In other words, anytime you go through those phase changes, heat is going to be released. Which ones are endothermic? Fusion, vaporization, and sublimation. Now this one's easier to memorize because if you think about it, let's say I want to turn ice into water. I want to melt ice. Well, wouldn't that require energy? Then heat would have to go into the ice cube. That would be endothermic. What about if you want to boil water? Well, wouldn't you have to heat up the water? Heat would have to go into the liquid. That would be endothermic. And same thing if you want to go from a solid to a gas, you'd have to heat up that solid. That would be endothermic. The other three are going the other direction. They're exothermic. So let's look at the phase change diagram again. And we can look at it this way. If you are going up the staircase in this direction, then heat is going to be added all throughout. This way would have to be endothermic. However, if you're going this direction down the staircase, then heat would have to be released. That would have to be exothermic. So an easy way to memorize it is to look at the direction it's going. This is great on a multiple choice test because if you're given a question like which one of these phase changes is exothermic and three are going one direction and one is going the other direction, pick the other direction. You're guaranteed to get it right. Now, the last thing I want to point out is that there are different parts of this graph. There are the diagonal parts and there are the flat line parts. The flat line parts are the phase changes. And you might notice that heat is increasing no matter where you are going up this staircase and decreasing no matter where you are going down the staircase. But what's weird about these two lines here is that in these two lines, even though heat is being increased or decreased, depending on which way you're going, there is no change in temperature. Why is that? Why is it that if I have an ice cube at this point right here and I heat it, literally put heat into the ice, it will eventually become a liquid, but there will be no change in temperature. The same thing is true if you put a thermometer in a glass of boiling water. That water will boil, but it will remain 100 degrees for the entire time it's boiling. Well, the reason for that is because of kinetic and potential energy. During a phase change, the flat line parts, potential energy changes. But kinetic energy does not change. Now, how do I know kinetic energy does not change? Well, didn't we define earlier that average kinetic energy is another word for temperature? So if the temperature is not changing, doesn't that mean that kinetic energy is also not changing? Sure. But what about during the solid, liquid, or gas phases when there's the diagonal part going up or down? Well, that means kinetic energy is changing. Now, how do I know kinetic energy is changing? Because the temperature is changing. But what about potential energy? Well, that is not changing because we already said that potential energy changes when there is a phase change, a flat line, not when there's a diagonal line. I also want to point one other thing about this diagram, that the vaporization line seems to be longer than the fusion line. Take a look. Here's the vaporization line, and look at the fusion line. It's smaller. Well, why is that? Well, that's because vaporization requires more energy than fusion. It simply takes more energy to turn a liquid to a gas than it does to take a solid and turn it into a liquid. And the final thing I want to point out is that even though I've shown you a heating curve, and this has all the information you could need about all the definitions, all the words, what if I were to show the exact opposite, a cooling curve? Well, let me just make a rough sketch of a cooling curve, and you'll see that there are no real surprises here. So we'll make this temperature, we'll make this heat, but this time let's start as a gas, which means it's going to be high. Up here is a high temperature. It will go down. Eventually, what's going to happen? It will start to condense into a liquid. Then when it's a liquid, it will go down, and it'll start to freeze into a solid. And then eventually, there you are. Notice it's the exact opposite of this picture, but it's still showing the same thing. We have gas, liquid, solid, and in between we have gas to liquid, which is condensation. We have liquid to solid, which is freezing. Or we could, of course, go the other direction. Again, the diagonal lines, there's a change in kinetic energy. The flat lines, the horizontal lines, there's a change in potential energy. The only difference between this picture and the other picture is in this picture, energy is going down, right? Here, a gas is becoming a liquid is becoming a solid. In the other one, solid's becoming a liquid, liquid's becoming gas. Here you're adding heat. Here, pretty much, you're taking away heat. It's decreasing, not increasing. So this way, heat's going down, and this way, heat's going up. And that's our lesson on phase change diagrams and heating and cooling curves.